Thank you, Maxime, for this very nice presentation. We have had two presentations. One was a combination of technology and ecology, very nice. Now, there is lots of room for improvement in the technology of membrane technology, and now we are going deeper down. We are now going to talk about the membrane. Robert Burk from United States, he will give you a lecture on nanocomposite nanofiltration membranes. He works with nano H2O, I think, and the title of his speech is Salt Rejection Improvements Using Seawater, using nanocomposite membranes. And this is, I think, another breakthrough in membrane technology. Robert, the floor is yours.
Thank you very much for the introduction, and thank you for inviting me to this conference. Let's see here. I think I'm going to have to. All right, got it. So anyway, I want to talk to you about salt rejection improvements on seawater nanocomposite membranes. These are reverse osmosis membranes, okay, and there is some confusion sometimes because we use the term nano, and there are also nanofiltration membranes, but these are actually conventional reverse osmosis membranes. And what I'd like to mention first is the importance of membranes in driving cost. Okay, membrane is the key, one of the keys in driving cost of desalination. I want to talk about nanocomposite membrane technology and how that relates to cost. A little bit about membrane performance. I'll show you some comparisons with other commercial membranes, and talk a little bit about the value of staging within a pressure vessel. So let's look at RO membranes and the sort of how the system works. So when we look at a conventional RO system, reverse osmosis system, you have a pressure vessel which has anywhere from 1 to 8 membrane elements in it. Okay, most commonly 5 to 8 membrane elements that are lined up in the pressure vessel, and then each pressure vessel is just repeated and repeated and repeated. So if you're at Ashkelon, let's say in Israel, you've got thousands and thousands and thousands of these same pressure vessels. It's a massively parallel sort of system, and you feed water in, and potable water comes out of the central tube at the end. But when you look at the cost, you're talking about a membrane element which is 5 to 10% of the capital cost of a plant, but it's driving 70 to 80% of the cost of producing desalinated water. And that's because you've got the permeability of the membrane characteristics drive the size of the pumps, it drives the size of the pretreatment. There's a whole bunch of different factors which are driven specifically by the membrane itself. And that's actually why I got interested in membranes. I hadn't been part of this before, but I saw desalination as something that was a way to produce drought-proof water supplies for communities, and also, but also they were it was a very capital intensive sort of way to do that. And so I was interested in what's the central issue that we could solve that would help with the economics of desalination, and kind of came down to the membrane and innovating on that membrane. So Let's talk a little bit about nanocomposite membranes and just what that means. Conventional reverse osmosis membrane has 3 layers, and this is true for all of the major membrane manufacturers. Okay, we all have 3 layers basically, and the first layer is a non-woven polyester. Okay, it's basically very similar to paper. It's you feel it, and it feels like paper. Okay, so non-woven polyester, and that's roughly 100 microns thick. Everybody buys it from one of the major manufacturers. There's one in the United States. Most of the rest of them are in Japan, and all of the major reverse osmosis membrane manufacturers buy this paper, buy this non-woven polyester. On top of that is cast a polysulfone support. Okay, and again, the polysulfone support is not very different among manufacturers. This is pretty standard stuff, and we cast it much like other manufacturers do. It's a water extraction process basically that casts the polysulfone onto the support layer. Now, once you have this big roll of support, okay, you have another machine that puts on a layer, a polymer layer. It's a polyamide, and this polymer layer basically there are 2 monomers. There's an organic monomer and an aqueous monomer, and when those 2 monomers contact each other, it's called interfacial polymerization. The polymer is formed. It's about 100 to 200 nanometers thick. And the innovation here for nanocomposite membranes is putting nanomaterials in that layer. Completely encapsulated within the layer are these nanomaterials. And what happens is you change the polymer structure. Okay, so you're now making a membrane which is more permeable. And if you go back to thinking about all those pressure vessels and the big pumps and so forth, now you can either lower the pressure or you can make more water because you've made this membrane more permeable. You've got a higher flux membrane. And one of the topics here is not only is it a higher flux membrane, but we've learned enough about the nanomaterials here in this top layer that we can actually increase salt rejection. Okay, and I'll talk a little bit more later about how that affects the membrane, or how that affects really the customer producing better water. Still standard module, so forth, and this is certified in the United States by kind of the key agency that does certification for potable water for health standards. Well, the development in nanocomposite membranes wasn't always so easy, okay? We started out, the first challenge was simply to make a good membrane without nanoparticles, and that was, these were all hand cast at that point, and we made a decent enough membrane, and then we got surface aggregates on the membrane, which is kind of shown in this picture, and that certainly wasn't working. We were not only not increasing the flux of the membrane, but we were getting lower rejection. And finally we managed to get aggregates of nanoparticles in the membrane, and we got a little more flux, but decreased rejection. Now, this was not a very happy time in the development of nanocomposite membranes. You're putting nanoparticles in, and you're getting a membrane which is not as good as the ones without nanoparticles. And the key in developing nanocomposites was really to learn about dispersion and to get the nanoparticles properly dispersed. And then go through, I was involved with going through about 100 different nanomaterials. Okay, so we basically went through a lot of materials trying to optimize the materials, and every time we optimize a little bit, we got a little bit better. And then finally, today, with a commercial fabrication facility that we have in Los Angeles in the United States, we are able to make a membrane which is really more than competitive with the other membranes that are out there. So to deal with these membranes, we have to do a lot of testing, and so we're still doing testing at the U.S. Navy Desalination Test Facility north of Los Angeles, California. And that facility has been running for 20-some years and is just a fabulous facility to be able to test membranes. So initially we tested some modules with respect to industry standards. There's some industry standard membranes which are a little over 22, almost 23 cubic meters per day, some that are 34 cubic meters per day, and have higher active area than we had at the time. We now have the same active area as these, but basically our element fluxes were considerably higher than some of the industry standard membranes. And what that means, what's significant to I think what most of us care about of water supplies, is that we're able to significantly reduce operating pressure and yet keep the same amount of water. So the system production can be the same, but the operating pressure is significantly lower, and we have a lot. I'll explain in a moment an example in the Caribbean where they're paying 29 cents a kilowatt hour for their energy, and you can believe that being able to lower the energy by 8 or 10 bars is a significant factor for them, even though it's 29 cents in U.S. dollars as opposed to euros. So the other way to look at this is operating at the same pressure. So here's an example where we took a standard membrane and operated at the same pressure and got 25% more water. So there's a balance here, and this is the factors here that are important are salinity and temperature, and so you don't always get these numbers at every place. Okay, so the takeaway here shouldn't be that you can always get 25% more water. That's not correct, but in some cases you certainly can, and usually what we find is people want some kind of balance between getting more water and saving on energy. It just depends on the specific customer. Now, when I look at what's out there in terms of membranes, the membranes that we're talking about, the thin film composite membranes, there are newer membranes that various companies have, and they've been working on this stuff for 30 years, and these are the newest ones. Our membranes, the nanocomposite membranes, you can see have greater specific flux. Okay, so this is LMH per bar, which is a way to sort of fairly compare everyone's membranes. So we're working on that. We have some membranes, our next generation. We have these which have even more flux. But as I'll explain in a minute, it's not always about having the highest flux if you're doing a retrofit. If you're retrofitting existing plants, you can't always look at it that way. So I think you have to be careful with saying higher flux is better. Higher flux is better if you're optimizing, you're building a new plant, and you can design for that higher flux. The other thing that really we've been able to do here, and we focused on Flux first, but nanocomposites also can give you better water quality, okay? And so that's something else, that these are lower flux membranes, lower productivity membranes, but with higher rejection. And that's part of the key of looking at these membranes. So so looking at high rejection nanocomposites, we've tried it, and we have these in the field now, but we've also tried it with 10 centimeter and 20 centimeter, and getting 99.85% rejection. And I think there's a trade-off here. There's always a trade-off between water permeability and salt permeability. Okay, so for a conventional membrane, you see that at low water permeability, there's very little salt permeability. At higher, there is more salt permeability. It's true for all membranes. It's true for nanocomposites as well. But what's happening here is that we're able to decrease the slope of this curve. That's really what we're able to do, and improving that salinity is pretty significant. So the market today, the best membranes that are on the market commercially, other than the ones that are produced by NanoH2O, they quote 99.8% salt rejection. So under these operational conditions, that's the ppm of total dissolved solids that you would get. If you're going to a 99.85% membrane, there's a 25% difference here, huge difference in the salinity of your product. So that's again part of the promise of these membranes. Now, I've got it here. I've got a presentation timer. Thanks. So and I need to hurry up. Yeah, I got it. Thanks. So at any rate, one of the ways to deal with system design, you can also, especially in retrofit situations. Oops. There we go. Sorry. You can make hybrid design. So I'm going to show you a diagram where we have elements of all of one type, all of another type. This particular one is relatively lower flux compared to this one. And when you have membranes lined up in a pressure vessel, remember I said that there was everywhere from 1 to 8 membranes, often sort of 5 to 7, 5 to 8 in these pressure vessels. You're taking fresh water and putting that into this central core tube. As you do that, you're basically increasing the amount of salt that the next membrane sees. Okay, so one of the solutions here that works very well is to have lower flux, high rejection membranes in the front, and very high flux membranes in the rear, and you balance your permeate flux throughout the entire pressure vessel. Okay, and that's very powerful. So let's take a look at what happens. So here's element position within a pressure vessel, and here is the individual element permeate flow. And so this is a very aggressive way of running a reverse osmosis system. No one would recommend this because your lead elements are running so hot. There's so much flux running through those lead elements that you're fouling those elements. On the other hand, if you cut down the the lead elements, you have lower flux membranes at the front of the pressure vessel, higher flux membranes at the end. You can run at very high system fluxes, which is much higher than what most membrane manufacturers would recommend. So let's look quickly at what you can do with this sort of system. Here's a customer, the Water Authority of Cayman in the Caribbean, south of the United States. And in this particular case, they really cared about energy. And so, we thought, well, we could put in nanocomposite membranes, and that'd be great. But you'd run your lead element flux too high if you did that. So we put in it was a stage system, and we put in a lower flux membrane up front. Here's where they were running before we put in the nanocomposites. Here's where we're running after the nanocomposites. To be fair, these were older membranes, and the real difference here is probably somewhere in the range of 3 kilowatt hours per cubic meter down to, the range here is 3 kilowatt hours per cubic meter down to about 2.5 meters per kilowatt hour if these were new membranes. But you can see that the nanocomposites made a huge difference. The Cayman Water Authority is very happy with that. We now have about 4 months of data, very stable data. When you look at the up and down here, it has to do with the pumps. I can talk to you about that and the way it actually has to do with saltwater intrusion and kind of akin to what the first speaker was talking about. At any rate, just to finish up, nanocomposite membranes do have the ability to lower the cost of desalination in new builds up to 20% less energy, or you can have more water, or you can decrease the footprint of the plant. Basically, I hope I've explained that there's ways to get more water, there's ways to get less energy, but certainly nanocomposites are what's not only new, but what is now moving into commercial use. Thank you very much.
Thank you, Robert. This is a nice example that even in a 40 years old business, we still can have breakthrough technologies, and we have new options in the design for seawater reverse osmosis.